Good morning all. In this section we are going to discuss about the maxima and minima of a function. This is the last topic of this chapter, application of derivatives. So maxima and minima of a function. What do you mean by maxima of a function and what do you mean by minima of a function? Or when can we say about its a maxima and a minima? Then one more point is there, what is the maximum value of a function and minimum value of a function? All these things we have discussed in this section, maxima and minima of a function. Okay, so what is a function, when can we say a function is maximum? Or when can we say a function said to have a minimum value? Okay, so that's we are going to discuss in this section. Let f be a function defined on an interval I. So a function is defined on a particular interval I. So function is defined on an interval. That is very important. Then first point, f is said to have a maximum value in I if there exists a point C in I such that f of C is greater than f of x for all x element of I. Then f is said to have a maximum value or f is said to have a maxima. Okay. Then there exists a particular point C in which the value of that function should always greater than the values of the remaining values in the domain, or domain means the remaining values in the interval I. Okay. So that is f of C should be greater than f of x. F of should be greater than f of x for all x element of I. Or simply we can say that f of C will be the highest value of the function. F of C will be the highest value of the function for all x element of I. Okay. The number f of C is called the maximum value of f, and the point C is called the point of maximum. C is called the point of maximum value. C is called a point of maximum value. Okay. So f is said to have a maximum value in I if there exists a point C in I such that f of C should be greater than f of x for all x element of I. That is, f of C will be the highest value of the function in the domain, or in the domain means in the interval. Okay. The f of C is called the maximum value and C is called the point of maximum value. Similarly, we can define the minimum. If we said to have a minimum value in I, there exists a point C in I such that f of C should be less than f of x for all x element of I. That is, f of C will be the lowest value in the interval. Okay. So f of C should be greater than f of x for all x element of I. Okay. Then f of C is called the minimum value and the point C is called the point of minimum value of f. Okay. Now, one more point is there. F is said to have an extreme value in I. Extreme means it can be maximum or minimum. If we said to have an extreme value in I, if there exists a point C in I such that f of C is either a maximum value or a minimum value f in I. So a function f has a maximum or minimum value, then we can say that it has an extreme value. Okay, a function f is said to have an extreme value, the function should have either a maximum value or a minimum value or both. Okay, the number f of C in this is called an extreme value of f in I, and the point C is called an extreme point. Okay, let's discuss this concept geometrically later. So I am going to discuss next point as local maxima or local minima. Local maxima or local minima. So what do you mean by local maximum? Local maximum means let f be a real valued function and c be an interior point in the domain of f. Then c is called a point of local maxima if there exists an h greater than 0 such that f of c should be greater than or equal to f of x for all x belongs to c minus h, c plus h. Okay. So while discussing this local maxima and local minima, I am going to give a geometrical interpretation of maximum value and minimum value. Okay, then we will come to the geometric interpretation of our local maxima or local minima. Okay, I am taking this space for this. Suppose there is x-axis and y-axis is there, x and y-axis is there. I am going to consider a function. Okay, suppose this is the graph of a function y is equal to f of x. Okay, here this function is defined from the interval a to b. Okay, see, this is the point c. C1 is the point there. Okay, and this point is C2. What about f of c1? F of c1 is the height of this curve, that is f of c1. Okay, we can see that this height or f of c1 value, the value of f of c1 is always greater than any other value in its domain. If we consider a point here, then the value is this one. Okay, suppose this is d is the point there. Okay, then f of d is this one. Okay, and I am taking this point as d2 or d2. Okay, then f of d2 is here. So if we take the value of the function at any point between the points a and b or between the interval a and b, the value of f of c1 should be always greater than any other value in the interval. Okay, so we can say that f of c1 is the maximum value of this function and c1 is called the point of maximum. Okay, similarly here see, we can see a point c2. We can find a point c2. In this point c2, the value of function is f of c2. This is the height here. Okay, this value is way smaller than any other value in the remaining part, isn't it? So we can say that c2 is called the minimum value, point of minimum value, and f of c2 is called the minimum value of the function. Okay, so here the height is this much. Then we know that this height is greater than every point, the value of the functions in every point in its domain. So we say that this point is called the point of point of maximum, and the value f of c1 is called the maximum value of the function. Okay, this is what about maximum and minimum value. Now we are going to discuss about the local maxima or local minima. Okay, so let's discuss about local maxima or local minima. Suppose I am going to consider a small part. Suppose this is the point C. Okay, it is a smaller value which is greater than 0. Then c plus h and c minus h will be here. Here c minus h, here it is c plus h. Okay. If we consider the values between this smaller interval, we can see that this point is always gives a greater value than the remaining values. So this point C is called the point of local maxima, because here f of c is greater than any other value between c minus h and c plus h. So it is an arbitrary value which is greater than 0 and it's very small value. Okay, then we can say that C minus h comma C plus h, the open interval C minus h comma C plus h gives a small interval. In this interval, f of c will be the highest value. So we say that C is called the point of local maxima. Similarly, suppose this is the function there. And I am going to consider this point as C. Okay. Then there is also interval C minus h or C plus h. Okay. This is the interval C minus h, C plus h. And we can see that this point is smaller than any other value between C minus h and C plus h. So we say that C is called the point of local minima. Okay. This is local because there is a small interval. While considering the minimum value and maximum value, we take the interval as the whole domain of the function. Here we are taking only a smaller part of the interval AB. Okay. So C minus h comma C plus h is the smaller interval and f of c is the highest value among the values between C minus h and C plus h. Then we say that C is called the point of local maxima and f of c is called the local maximum value. And if f of c is less than 0 for any values between C minus h and C plus h, where C minus h and C plus h, the open interval C minus h, C plus h is a smaller interval between the domain, okay, then C is called the point of local minima. A function have so many local maxima, local minima, but a function have only a maximum value or a minimum value. Okay. So let's discuss the local maxima, definition of local maxima and local minima theoretically. F be a real valued function and C be an interior point in its domain F, then C is called a point of local maxima if there exists h greater than 0. H is a smaller value which is positive, h greater than 0 such that f of c is always greater than or equal to f of x for all x element of C minus h comma C plus h. Okay, where it is given that x not equal to c. And the value f of c is called the local maximum value of f. Similarly, c is called a point of local minima if there exists h greater than 0 such that f of c should be less than or equal to f of x for all x element of C minus h comma C plus h. Okay. The value f of c is called the local minimum value of f. So here please be noted that x not equal to c is the condition there. X not equal to c. Why x not equal to c? Then f of x becomes f of c. So that is what we are saying, that f of x is equal to f of c means it's a constant value. Okay. So the point of local maxima or local minima, it does not have this inequality sign. Okay. This inequality won't be there. Okay. This inequality won't be there. F of c greater than f of x for all x in C minus h comma C plus h. Or if we write x greater than or equal to c, f of c greater than or equal to f of x, then we have to mention x not equal to c there. Otherwise, f of c greater than f of x for all x element of C minus h comma C plus h. It is enough for the definition. Okay. So this is called the definition of local maxima or local minima. Okay. Now let's go to the graphical interpretation of a local maxima and a local minima. See, here the function is decreasing. At this point, the function is going to become to increase. Okay. So the graph is coming like this, that is graph is in decreasing way, and at this particular point, the graph is going to increase and reaches at this point. Okay. At that point, see, at that point we can see that the graph is going to decrease. So graph is decreasing. At this point the graph is going to increase, and when it comes here, the graph is going to decreasing. Again it is coming to this point, again it is going to increase. See, At this point, the function gives a local minima. Because at this interval, here I am, suppose this is taking as C1, then C1 plus H is there and C1 minus H is here. At this interval, f of c, this is the value f of c. F of c is less than for any other value between c minus h and c plus h. So this is known as local minimum. Okay. Or we can say that where the point is changing its continuity, that is increasing to decreasing or decreasing to increasing, at that point is called the point of local maximum or local minimum. This is the geometric interpretation of this local maxima or local minima. See, here local maximum value is this one. So because the function is increasing, at this point the function is going to decrease. This point is called local maxima. If the function is decreasing and at a particular point, if a function is going to increase, then we get a local minima there. Okay. So we can say that increasing to decreasing gives local maxima. Local maxima. Okay. And decreasing to increasing gives local minima. Okay. So this is the condition for local maxima or local minima. Okay. So this is the best graphical interpretation of local maxima or local minima. We can see here it is local minima, here it is local maxima, here it is local minima. Suppose the graph is going this way. From here, the graph is coming to this way, then coming to here. Then at this point, the point we get local maxima because the function is increasing, then coming to decrease. Okay. So at this point, we get a local maxima. If it is going this way, we can say that at this point, we get a local minima. Okay. Now what are the ways to find out a function has a maximum or minimum value? The first method is first derivative test. By using first derivative test or by using first derivative, we say that the function has local maxima or local minima. A function, let f be a function defined on an open interval I. Suppose f is a function defined on an open interval I. Let f be continuous at a critical point C in I. So if it's continuous means it has no break. Okay. F dash x changes its sign from positive to negative as x increases through C. That is, f dash x greater than 0 at every point sufficiently close to A and to the left of C. Close to and to the left of C. And f dash x less than 0 at every point sufficiently close to and to right of C, then C is called a point of local maxima. That's what we give the geometric interpretation. Because if a function is going like this, see, suppose this is a function, this is the point C there. Okay. Here f dash x changes its sign from positive to negative as x increases through C. As x increases through C. If that is, if f dash x greater than 0 at every point sufficiently close to and to the left of C. Because the left of C, the function becomes increasing. Okay. Because slope of the tangent will be positive. That is, dy by dx should be positive. Okay. So we know that if a function is increasing, then the first derivative should be greater than 0. So that is what here saying that f dash x changes its sign. Here now the f dash x is positive. At this point f dash x is positive. Okay. here f dash x is positive. Here it is positive. Because the slope of the tangent is positive here. Okay. After C, suppose after C, what happened? Slope tangent will be like this. Then it makes an angle which is greater than 90 degrees. So tan theta should be negative. And we know that if a function is in decreasing way, f dash x should be negative value. So that is first derivative is negative. First derivative negative means here the slope of the tangent is negative. So f dash x here greater than 0, but here f dash x less than 0. See? So then the point C is called, then we can say that the point C is called a point of local maximum. That's what here defined. If f dash is greater than 0 at every point is sufficiently close to and the left of C, close to and the left of C, and f dash x less than 0 to at every point is sufficiently close to and the right of C, then C is called a point of local maxima. Then C is called a point of local maxima. Okay. So let's discuss the next condition. Second thing is, if f dash x changes its sign from negative to positive as x increases through C, that is, f dash x less than 0 at every point sufficiently close to A, so close to and left of C, and f dash x greater than 0 at every point sufficiently close to and to the right of C, then C is called a point of local minimum. Okay, let's see how it is possible. See, I am going to consider a graph like this. Here, this is the point C. Okay. To left of C, the slope of the tangent will be negative because the graph is in decreasing way. And the right of C, the slope of tangent should be greater than 0 because the graph is increasing. So, graph or f of x changes its sign. So, f dash x changes its sign from negative to positive. Then we get a point of local minimum. From positive to negative, we get a point of local maximum. Okay. So, f dash x changes its sign from negative to positive, then we get a local minima, and positive to negative, then we get a local maxima. That's what about the first derivative test. And sometimes the derivative becomes 0 through the point. Then we say that the function is a constant function. Since the derivative becomes 0 means it is going like this. The tangent is going parallel to x-axis. Okay. So at that point the function does not have any maximum or minimum. Okay. So that's what we are going to discuss next. F dash x does not change sign as x increases through C. Then C is neither a local maxima nor a point of local minima. In fact, such a point is called a point of inflection. This point is called a point of inflection. This point is called a point of inflection. Okay. Suppose sometimes f dash x does not change its sign as x increases through C, then C is neither a point of local maxima or a point of local minima. Such a point is called a point of inflection. Now we are going to discuss about the second derivative test. The most important and continuously using test for finding the maxima and minima of a function is second derivative test. So it is that much very important. Because the first derivative test we don't usually applied in most of the all problems. When a second derivative test fails, only we use the first derivative test, whether the function is maximum or minimum at that particular point. So this second derivative test is the very important. It is the major important and continuously applying method to find out the maximum and minimum of a function. So it is that much very important. Second derivative test. It is very easy one actually. To find a point is said to have a local maxima or local minima, or a point is said to have a maximum or minimum at for a function at that particular point. We use the second derivative test to find out. What is second derivative test? Let f be a function defined on an interval I. Okay, f be a function defined on an interval I, and c element of I. C is a point in I. C is a particular point in I. Let f be twice differentiable at C, then exists a point of local maxima if f dot C is equal to 0 and f dot C less than 0. C is called a point of local maxima if f dot C is f dot C is equal to 0. First derivative should be equal to 0 and the second derivative should be in negative value. So it is less than 0, negative. Okay, it is very important. If a function f of x is said to have a point of local maxima if f dash x, the first derivative is equal to 0 and the second derivative should be negative. And in case of local minima, f dot c is equal to 0, first derivative is equal to 0, but the second derivative always greater than 0. Okay, and if the test fails if f dot c is equal to 0 and f dot c is also equal to 0. So that is what second derivative test. So a point C is called a point of local maxima. First we have to find out the first derivative f dot c, then take it as a 0, then find out f dot c. If the second derivative value is less than 0, we get a negative value at that particular point C, then we say that the point is that point is a local minimum value, so now local maximum value, and f dot c is greater than 0. F dot c is greater than 0, that means positive. Then we say that that point is a local minimum point. So when second derivative is negative, then we get a maximum, and if the second derivative is positive, then we get a minimum.